Yeah, I will say, guys, definitely marry above you so that things work out well for you the rest of your life. Yeah, we're starting 9.1. My wife actually told me, and this is recording now, but we were driving the car, and I was driving, like always, and she says, you know what, I was just reading a study that said that if the husband dies before the wife, or she actually said the other way around, if the wife dies before the husband, bless you, the husband either A, gets married again right away really fast, or slowly degenerates and dies, right? Like the man needs the woman. And then she said, but they found that if the man dies first, the wife actually thrives and gets stronger, and starts becoming more and more happy and taking over the world. So, oh, maybe so. I don't know. I took it to be I am the dead weight in the relationship. I'm the anchor that's holding her down. So anyway, but I need her. So 9.1, sequences and series. Convergence and divergence. All right, so we've already talked about convergence and divergence when we talked about improper integrals, right? If the integrals approach the finite number, we say that the integrals converge, and if they either approached infinity, negative infinity, or oscillated, we say it diverged. We're going to do the same thing now, but we're going to do it with sequences and series. So series is where it's all going. It's all focused on the series. But to set up the series, we're going to talk about a sequence. So what is a sequence outside of math class? A pattern. What? We took a lunch. Yeah. So a sequence would be like I did this, and then I did this, and then I did this, right? So if you have a sequence, it is a list of things. Does the order matter? Yeah, for the most part it does, even outside of math context. But in a math context, the order really, really matters. So here's what a math sequence is. It's a list of things generated by a rule, okay? And the rule is typically an equation. It's an equation of a function of n, where n, as it says here, is an element of the counting numbers or the natural numbers. We start counting with the number 1. We didn't know there was 0 until we started getting jealous of people who had more than we did, and then we realized we had none. But the first number that we naturally started counting with was 1, okay? So what n ends up being is the domain, the natural numbers end up being the domain of our rules of sequence. So here would be a way to list a sequence. We call the A's the terms. These are the terms in the sequence. And so A sub 1 would be the first term. So the index or the subscript is the counter. It denotes which term it is. And we always start with number 1. So A sub 1 is the first term. Comma, we separate the terms with commas. A sub 2 is the second term. A sub 3 is the third term. And then we put ... And A sub n is called the nth term. And then the comma should be back on the ground floor, ... not in the subscript. I messed that up. So that's called the nth term or the rule of sequence. That's the equation. That's a function of n, and where n is a natural number, okay? And it gives you the way to generate the next term. All right, so we can list a sequence or express it by I'll add 4 ways to it, okay, one of 4 ways. Number 1, an ample or sufficient number of terms in the sequence, separated by commas. So for instance, 1, 2. Would that be a sufficient number of terms to, bless you, predict the next term? No, the third term could be anything. But if I put 1, 2, 3, now that's enough to say, okay, the next term is probably 4. So 3 would be the bare minimum. That's the minimum number of terms. 3 terms minimum. If the pattern that generates the next term is sufficiently difficult, you might add a 4th term or a 5th term to give more evidence to how they're generated. So there you go, 1, 2, 3, ... That would be one way to list the sequence or express the sequence. Another way would be an explicit function defined by a rule of sequence. So that would be like defining A sub n equals something like n plus 1. Okay, so this is explicitly saying A sub n, the nth term, is n plus 1. Or you could set it off in braces. Okay, so If you see something like this, n plus 1, that means that it's a rule of sequence, or that's the nth term. And the fourth way would be in the list, which would be something like, if let's just say we had it as n plus 1, then we always start with n equals 1, okay? So the first term would be 1 plus 1, which is 2. The next term, when n is 2, would be 3, comma 4, comma, dot, dot, dot. You could put the rule of sequence right there, plus dot, dot, dot. So that would be the fourth way. Listing a sufficient number of terms, and then listing the rule of sequence of the nth term somewhere down the line, comma, followed by dot, dot, dot. So a lot of different ways to list that. But at the bare minimum, you just list it like this, and there is no rule. So sometimes we have to figure out what the rule is, and that's kind of fun, okay? So let's look at example 1. The sequence 2, 4, 6, 8, comma, dot, dot, dot. Can anyone predict the next number? 10, all right? It is 10. These are the even numbers. What we want to try to do, or successfully do, is write the rule that generates it. Okay, so we got to keep in mind that 2 represents the first term. So it corresponds with n equals 1. That's n equals 2. Yeah. So what equation then, when we use those n values, will give us those numbers? 2n. Yeah. So I'm going to go ahead and list it like that. That's one way to do it. Or we can say that it equals 2n. So either one of those say the exact same thing. Whenever you see something like this, it's implied that n always starts with 1, and it's also implied that we're counting by positive integers. So when we look at functions like 2x, it's all real numbers, negative infinity to infinity, and it includes everything between the numbers on the number line. But when we say 2n, n is 1, 2, 3, 4, so on and so forth. So a much smaller type of infinity for the domain. Okay, the next thing, 1, 3, 5. I only listed 3 this time. What's the next number? 7. Okay, good. So 1, 3, 5, comma, dot, 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 comma. Let's see if we can figure out a rule of sequence, or the nth term, that will generate that. Remember, 1 has to correspond with n equals 1. It's the first term. 2n minus 1? Yeah. It's either 2n plus 1 or 2n minus 1. So you can kind of do guess and check. When n is 1, you plug it in, you get 2. You need to subtract 1 to get 1. When n is 2, you get 4 minus 1 is 3. There you go. So even numbers are generally of the form 2 times n, and odd numbers are generally 2n minus 1 or 2n plus 1, depending on where you want to start. Okay, cool. You could also write it like this. Now, how many terms are in each of these sequences? The terms are the things that we're listing between the commas. Infinitely many. So we call these infinite sequences. Infinite sequences. Okay, and again, when you write the general term, you have to have the ellipsis points. That's what we call them on either side. So what we're going to be primarily interested in then is, for these infinite sequences, these list of terms, do the sequences converge or do they diverge? Yeah, both of these we could probably easily say diverge, right? They both diverge to infinity, right? 2, 4, 6, 8, 10, blah, 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 to infinity, and 1, 3, 5, 7, 9, blah, 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 to infinity. So let's go ahead and do example 2. This is kind of a hybrid way to do it, and I probably should do one or the other. It should either be a sub n equals 4n over 3 plus 2n, or it should be this. So I have a little bit of improving to do on my notes, but we'll make those adjustments accordingly. So anyway, there's 2 different ways to list the sequence. It says to list out the first 5 terms and then estimate what the limit is as n goes to infinity. Okay. So each of these then we could just put an equal sign because they're equivalent. So we start with n equals what? 1. Always implied n equals 1. So I'll just plug it in over here. I get 4 in the top over 5 in the bottom. So there's the first term. When n is 2, we get 8 over what? 7. When n is 3, we get 12 over 9. When n is 4, we get 16 over 11. When n is 5, we get 20 over 13. And then we'll put comma, dot, dot, dot. And you could stop there. Now notice if I had just given you those 5 terms, it would be a little bit more difficult to try to come up with the rule of sequence or the nth term. So thank goodness it was given. You could stop there, or you could go ahead and throw the nth term back in there, which is, it's kind of nice to have that. If you have that or you found it, you kind of want to preserve that, because that's the essence, that's the DNA of the sequence. If you need more terms, that's how you generate them. All right, so now we want to find the limit as n goes to infinity. So to use the right notation, if we just looked at this, if we didn't have the rule of sequence, and we just saw 4/5, 8/7, 12/9, 16/11, 20/13, you could see that the ratios themselves are getting bigger, right? 4/5 is less than 1, 8/7 is a little bit bigger than 1, 12/9 is a little bigger than 1. So I can tell they're getting bigger, but how big are they going to get? Are they going to get infinitely large approaching infinity? Or are they going to get larger and larger approaching some limiting value? It's really hard to tell if you just have the terms, but if you have the rule of sequence, it makes it a little bit easier, because now we're just doing this. What's the limit as n goes to infinity? A 4n over, I'm going to rewrite the bottom as 2n plus 3. Do we know what the answer to this is? It's 2. So we can rely on our old skills of evaluating limits with x, all real numbers. It's really the same task here, even though we're talking about positive values of n. We have n to the first over n to the first. L'Hopital's rule would work here. When you plug in, you get infinity over infinity, but we have an easier way to do it. When the degrees are the same, it's leading coefficient over leading coefficient. So because the limit as n goes to infinity is 2, we say that this sequence, the sequence converges. And it converges to 2. Now you don't do this. You don't say equals 2. That would be incorrect. You don't say the sequence equals 2. And you certainly don't just put ... and put 2 and then stop. Okay? So you either write it as the limit, or you say the sequence converges to 2. Now notice, if I were to also give you just these first 5 terms, this 12/9 simplifies down. If I were to simplify 12/9, you might actually lose the pattern. So it's very often the case when you're expected to find the pattern that you'll see terms kind of in an unsimplified form. And that's to help you kind of see the correlation from one term to the next and how that relates to increasing values of n. Okay, so that's going to be our primary concern for the first part of this section. We want to know if these sequences converge or diverge, which means every time we're going to be interested in finding the limit as n goes to positive infinity. We can't even approach negative infinity, can we? Because n is a natural number. All right, so if we look at the right n behavior of each of these sequences, that is, find the limit as n goes to infinity, there's only a handful of things that are going to happen. The terms are either going to get infinitely large, in which case we say the sequence diverges to infinity, just like the integrals did. They could get infinitely small, to negative infinity. You can have negative terms. You'd say the sequence then diverges to negative infinity. They can approach a finite number, like 2, like ours just did, in which case we say that they approach 2, or they converge to 2, and they can also oscillate between 2 fixed numbers, or you'll see later actually 2 infinitely large numbers, and we say it diverges by oscillation. It's kind of interesting when, if you were to map or graph 4n over 2n plus 3 in sequential mode, what's going to happen is as we go out to infinity, you're going to get these values. Here's y equals 2. You're going to get these values that look like this. And we don't use it a lot, but if you have been paying attention, when you go to your calculator, you go down to that row, function, parametric, polar, the last one is SEQ, that's sequence. You can actually go to sequential mode, hit y equals, and type in 4n over 2n plus 3. And what it does is it gives you dots. It won't connect the dots with lines because that's not what we're doing. And it'll only graph it for positive values of n. But you can still clearly see that there's an asymptote there, right? If you were to connect the dots, it would be approaching, that's 2, not just y minus 2. Okay, so that's the difference between a sequence and then a function. We're looking at single points for positive values of n. All right, definition that's going to show up. And we've seen this before. n exclamation point mathematically is read as n factorial, and it's defined recursively like this. N factorial is n times n minus 1 factorial. That means 5 factorial is 5 times 4 factorial. Well, what's 4 factorial? Well, 4 factorial is 4 times 3 factorial. So you can define it like this as well. In general, n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4, all the way down until you get 3 times 2 times 1. You stop at 1, because if you went down to the next value of 0, what would happen to the whole thing? It becomes 0. So it's basically the product of every natural number up to and including that number there. So here's another example. 9 factorial is equal to that. So where does it come from? Why does it exist? It's defined in probability to be n factorial is the number of unique ways to arrange n objects. That's what it's defined as, to arrange n objects. To arrange n objects. N, yeah. So let's say, for instance, we have 4 factorial. If I had 1, 2, 3, 4 slots, how many different unique combinations can I have? Well, if there's 4 slots, there's, let's say 4 things. I have 4 objects. There are 4 ways I could place the first object. And now that object is placed, which means there's only 3 objects left over, which means I have 3 possibilities for the next slot. Once that one's taken up, I only have 2 objects left, so there's only 2 ways that I can do that. And now there's only 1 left over, so there's only 1 way that that last one can go. And so it shows up a lot in probability, and that's why there's a notation for it then as well. Now it's kind of interesting. What is 1 factorial? 1, right? 0 is not a natural number, but 0, believe it or not, is in the domain of n factorial. What do you think 0 factorial is? Most people think it's 0. But let's think of it in terms of its a verbal definition. There's only 1 way to arrange 1 object, right? Here, there it is. How many ways are there, though, to arrange 0 objects? There's 1 way to arrange 0 objects. You can't, right? And that's still a way. So it turns out, and your calculator knows this as well, 0 does not equal 1, but 0 factorial equals 1 factorial. That's awesome. So I always thought it would be a perfect time for like some administrator who doesn't know math to walk in right now, and they would say, okay, 0 doesn't equal 1, I get it. But in math class, apparently, if you say something with enough conviction and enthusiasm, it can be true. 0 is equal to 1, right? Because they don't know what the factorial means, right? Now, we can actually prove it recursively. Watch. 1 factorial, by this recursive definition, is equal to 1 times 1 minus 1 factorial. Well, that's 1 times 0 factorial, which is 0 factorial. So we just proved that 1 factorial, which we know is 1, is equal to 0 factorial. Pretty cool. That's kind of cool. I think so. And there is a factorial button on your calculator. You hit math, and then you click left or right to PRB, probability, and I think it's like number 4. So math, probability 4, something like that. Okay, sweet. Example 3. We're going to go through A, B, C, D, E, F, G, H, I, J, K, L, and we're going to determine if the following sequences converge or diverge. That's what we're after, which means in each case, we're performing that operation. We're taking the limit as n goes to infinity. It would be super nice if we had the rule of sequence. Let's see if we're so fortunate. All right, so here are the terms. 1/2, 2/3, 3/4, 4/5. You can see they're getting better. Hey, we have the rule of sequence there. So with the right notation, we'll do it for the first few of them here. Since we have the rule of sequence, the nth term, we could just write it down like that. And of course, what's the answer? 1. There you go. So we could say that this sequence converges to 1. So it's nothing new that we're doing. We're just doing it with n's instead of x's, all right? No, if it diverges, it would be infinity, negative infinity, or oscillation. It could still converge to a negative number. Okay, the next one, 1/2, 1/4, 1/8, and 16th. Now, if you didn't have the nth term there, you could probably still infer that they're getting really small, really fast, approaching 0. And you could probably also figure out the rule of sequence. But with the rule of sequence there, it makes it just a lot more definitive. You don't have to guess anymore, right? We know that that's a constant over an exponential, essentially, which means that it does go to 0. And it goes to 0 pretty quickly. Now, it's interesting because it is an exponential function on the bottom, and you can write the whole thing as 1/2 to the n. We're going to call this actually a geometric sequence here soon enough. Geometric sequence. All right, letter C. Now we don't have any terms listed. We just have 3 plus or minus -1 to the nth power. Do you think it converges or diverges? Well, let's see. What is this guy going to do? When n is 1, it's -1. When n is 2, it's +1. When n is 3, it's -1 again. When it's 4, this term right here is called an oscillator. It's an oscillator. All it does is it changes the sign. It doesn't contribute anything to a magnitude. It's either a 1 or a -1. That's it. Okay, it's a 1 or a -1. So if you're not sure, sometimes it's actually helpful to have the terms listed out. So let's go ahead and start listing some of the terms. When n is 1, we get 3 minus 1, which is 2. Comma, when n is 2, we get 3 plus 1, which is 4. When n is 3, we're back to 3 minus 1, which is 2. When n is 4, we get 3 plus 1, which is 4. 2, 4, 2, 4, comma, comma, comma. What do you think? Yeah, this one diverges. And it diverges by oscillation. So not to anything, infinity or negative infinity. So in this case here, we don't even have to write the limit. We're not going to write the limit anymore. We just are going to say now, diverges or converges. Okay? Letter D. Do this one very quickly. Without listing terms, do we know what it converges or diverges? Converges, right, to -1/2. Good. So again, this would be n to the first over n to the first. The leading coefficient is 1, and the leading coefficient is -2. So this one does converge to a negative number. All right. How about the next one? A sub n is ln of n, natural log of n over n. There we go. Well, let's see. If we actually write it out, ln of n over n, direct substitution gives you infinity over infinity. You could use L'Hopital's rule. Or you can remember the sequence of growth for functions. Let's go ahead and review that again. From slow growing to the fastest growing. You have constants k, and then marginally faster are your family of log functions. Log of x. We'll say log of n. We'll keep it all in terms of n now. And then you have your power functions that are like, I'll keep it as x to the n. How about n to the 8th power? Instead of x to the n, that'll be like n to the first, n to the second, n to the 1/2, your power functions. And then you have exponential of the form b to the n. And then you have your factorials, remember. And then you have your Aleph functions. Back then it was x to the x, but now it's n to the nth power. So if you ever see a ratio of something to the left divided by something to the right, it's going to be 0. All right, this would be the big O function in discrete mathematics. So which grows faster, linear or logarithmic, essentially? Linear, right? So this whole thing, do we say equals 0? Is that what we do? Right, we don't do that. We say it converges to 0. Or if you wrote the limit, you could say the limit is 0. So the sequence converges to 0. All right, cool. N factorial over n plus 2 factorial. We got a factorial divided by a factorial. They grow, they're part of the same family. So we know if it were like n cubed over n cubed, it would be leading coefficient over leading coefficient. If it were n cubed over n to the 4th, it would be 0. But how do we contend with 2 factorials? Any idea? Anyone want to guess? 0, infinity, or 5 maybe? 0? It's a good guess. Yeah? That's actually correct. Yeah. Here's a pretty common thing that we're going to be doing in this section a lot.
I'm sorry.
Oh, that's all right.
Did you say retest
Thursday, yeah. Yeah, Thursday morning. Which one is bigger, n or n plus 2? N plus 2. So because of the recursive nature of factorials, if you start with the larger one and start writing it recursively down, n plus 2 factorial is n plus 2 times n plus 1 times n minus 1 times n minus 2 times n minus 3. As soon as I get to the factor in the top, I can stop the recursiveness by tying it off with the factorial, right? So n plus 2 factorial is n plus 2 times n plus 1 times n factorial. Sweet. What happens with the n factorials now? They divide out all the way down the line. All of them. And we're really left with 1 over an n squared, which would be like our old 1 over x squared. So now the bottom grows faster, and the series what? Converges to 0. Yeah. Yes, n factorial you could think of as a parent function, but it doesn't have a smooth connected graph because we only graph it in sequential mode. So maybe at the end of class we'll go to sequential mode and we'll graph n factorial. We'll see what it looks like. It grows faster than exponentials for large values. Okay, that's a good idea. All right, letter G, 2n factorial over n minus 1 factorial. Well, first of all, is that 2 times n factorial, or is it the quantity 2n factorial? Just n factorial, right. Because if you wanted it to be the quantity 2n factorial, you would have had to have the parentheses there. So which one's bigger, n or n minus 1? N, right? So let's write the top as 2 times n minus 1 factorial. All over n minus 1 factorial. If the bottom had been n minus 2 factorial, we would have written the top as n times n minus 1 times n minus 2 factorial. So that we can get the factorial factors to match, and now, which is all the way down the line. And so we're left with just 2n. This thing grows basically like the line 2x, but with dots instead of lines. So we know this does what? Diverges to infinity, right? It gets infinitely large in the positive direction. All right, let's see. We're in here now till 1:15. Okay, good. H is next. Ooh, we have this little alternator now, but it's part of a single term in the numerator. Any ideas what to do to? Yeah, that's the strategy right there. Let's split it up. We can split up numerator. So we get n over n plus the alternator negative 1 to the n over n. And I can simplify that. That's going to be 1 plus negative 1 over n to the n. Now, remember, we're taking the limit as n goes to infinity. So we can look at this last piece over here. The top is going to be just a plus 1 minus 1, plus 1 minus 1, plus 1 minus 1. But the 1 over n by itself would go to what? 0, wouldn't it? 1 over n would go to 0. So what this thing is actually doing is it is going to 0, but it's jumping back and forth, like a positive 1, and then it would be positive 1, negative 1, sorry. Let's do it this way. It'll be like a negative 1, and then a positive 1/2, and a negative 1/3, and a positive 1/4, and a negative 1/5, and a positive 1/6. So it's doing this. And we're not connecting them, right? When we had sine and cosine, we connected them, right? But we don't do that here for sequences. But you could tell that they're still approaching what? 0. So this thing still approaches 0. So what does 1 plus 0 approach? 1. So remember, we don't say a sub n equals 1. We just say, unless we want to write the limit, we just say that this converges to 1. So these make great multiple choice questions, right? One of those multiple choice questions where you're given like Roman numeral 1, 2, and 3, and they'll give you some of these, and the instruction will say which of these 3 converges, and then your answer choices are any combinations of them. Or it could even say which ones diverge. All right, next one. We have a rule sequence given, but now the alternator is a factor in the numerator. Any ideas? Well, because it's only a negative 1 to the n and not like a negative 2. If it were negative 2 to the n, we got to be careful because now it's changing the sign and it's contributing to the magnitude. But it's just a negative 1 to the n, so it's only changing the sign. So if you focus on everything that's not the alternator, what would n minus 1 over n approach by itself? It would be n to the first over n to the first. It would be leading coefficient over leading coefficient. It would approach 1. So what's happening then if the piece in front of it is just changing the sign? When n is 1, it's going to be a negative 1. It's going to eventually approach something that's going negative 1, positive 1, negative 1, positive 1, negative 1, positive 1. Now, it's never going to actually be 1, negative 1, but it's approaching 1, negative 1, 1, negative 1. So guess what we could say? Yeah, we could say it diverges by oscillation. So remember when we had improper integrals? I said your intuition will take you far. It'll take you a long way. Same thing here. Your intuition can be your guide as to what the actual sequence is doing. All right, how about this one? We had a simple ratio of essentially an exponential to a factorial. Which one grows faster? Factorial. So this one converges to 0. All right, letter K. If we took the limit as n goes to infinity, the inside is approaching 1 while the exponent is approaching infinity. One due to the infinite power. That's indeterminate. Right. So what we're going to have to do, if we don't know what it is, we're going to have to go ahead and actually set up the limit. The limit as n goes to infinity of 1 plus 1 over n to the nth power. And because we have to take the natural log of both sides, we're going to have to set it equal to y. So we're after y. We want to know what y is. What is y? Okay. But now I can take the natural log of both sides. We did this with improper integrals and L'Hopital's rule. So now with the natural log there, I could say it's 1 plus 1 over n, and now the power of n can come out front. And now when you plug it in, you get the natural log of 1, which is 0 times infinity, which is still an indeterminate form. But we're making progress, because now it's the product form instead of the exponential form. So all we have to do now is turn it into the quotient form, and we did that by moving the n to the denominator, which makes it now n to the negative first. And remember, we're still bringing down the left side, the natural log of y. So now you get 0 over 0, which is one of the two acceptable L'Hopital forms. So we'll then use L'Hopital's rule on the right side only. This is not log diff. We're not taking the derivative both sides. But the derivative of the top is the natural log of blob, so it's 1 over that blob, times the chain rule, the derivative of the blob, which is 0, plus, and then that's really n to the negative first, so it's negative n to the negative second. And on the bottom, hey, I have n to the negative first, so that's going to be negative n to the negative second. And then those divide out. And we plug in an infinity to what's left, and we get 1 over 1, which is 1. So remember, in L'Hopital's rule, 1 would be an answer choice. But is that our answer? No, that's natural log of y. And now if we e both sides, we get y equals e. So, whoa, it turns out that the limit, as n goes to infinity, of 1 plus 1 over n to the nth power is one of the many definitions of e. Okay? That's the definition of e. So we saw this in the improper integral or L'Hopital's form, except it was 1 plus 2 over n to the nth powered, and the answer ended up being e squared. So the function e to the x looks like this. Limit as n goes to infinity of 1 plus x over n to the nth power. That's the function e to the x. So in the case where x is 1, we get e itself. The number e, Euler's number. Okay? And unfortunately, pi always has its day every March, right? But remember, E is arguably more famous, or not more famous, because more people know about pi than E, but maybe we value it more because, you know, we don't care for geometry as much as we care for calculus. But unfortunately, E never has his calendar day, right? If it did occur, it would be on February the 71st. And of all days to try and make a month go longer, February would be the hardest one to pull off. Right, with only 28 days. So, I don't know, maybe quietly we count forward from the 28th day and we go into another month and then we have a real quiet celebration for E. Yeah, with a small group of friends that don't judge too much, right? It would be close to today, wouldn't it? It'd be somewhere in April. Okay, today is E-Day, everybody. Hey. It's also Moose Day, and moose also has an E in it. Is that a coincidence? Totally. Yeah, totally. Okay. Anyway, it's Chocolate Moose Day. What'd you get? Oh, we missed like the Galactic E-Day. 02718. Dang it. That won't happen again for another 100 years. Okay. All right. We need to plan ahead next time. Remember, I can't even remember if I have a doctor's appointment on a given day, much less plan ahead 100 years. So anyway, put my wife to the task and it'll happen. All right. So this is the definition of E. All right. How about this one? This is the last one. Does this sequence converge or diverge? Notice there's no A sub n equals because it's just in braces. Yeah, this one converges to 0. Because we have a factorial, which grows pretty darn fast, over an Aleph function. Aleph naught, Aleph 1, Aleph 2, end of the n, end of the end of the n, end of the end of the end of the end of the n, and so it goes to 0. All right, sweet. Sometimes, albeit rarely, we have to write our own rule of sequence as a function of n from the pattern. This is the stuff that in part makes up IQ tests. How quickly can you see patterns? Some people faster than others. I know the sun comes up every day. I notice that. Okay. Write an expression for the nth term. 3, 8, 13, 18. What comes next? 23. Holy moly. How'd you get that? Okay, sweet. See, so some people see it faster than others. I was going to say like 72. I don't know. Here are the two basic patterns that you want to try. First of all, do you add or subtract to get the next term? Here's how you determine that. You take a term on the right and you subtract a term on the left. So what's 8 minus 3? 5. What's 13 minus 8? 5. What's 18 minus 13? 5. That means you're adding 5 to get to the next term. If you ever add or subtract a number to get to the next term, we call this an arithmetic sequence. Or if you mispronounce it, arithmetic sequence. When it's an adjective, it's arithmetic. You can put a little accent there, like it's in Mexico. Arithmetic sequence. Now, back in geometry, and I know you learned this in geometry because my daughter did this earlier in the year. Maybe not for infinite sequences, but there is a way to come up with the nth term. There's a rule, there's a pattern, a formula you can memorize, but you don't have to memorize it because you're smart. We know if we're adding 5 over and over and over again, what process do we call repetitive addition? Multiplication, right? So if we're adding 5 over and over again, that's like multiplying by 5. So you could say it's 5n, and then just make an adjustment, right? When n equals 1, we have to get a what? A 3. So now if I plug in a 1 for n, 5 times 1 is 5, I need to subtract what to get 3? 2. So you do that, and then you see if it works. Now when n equals 2, you get 10 minus 2, which is 8. When n equals 3, you get 15 minus 2, which is 13. Boom. So that's an arithmetic sequence. You add or subtract to get the next one. Now, if you try that and it doesn't work, the next thing to try is what you'll try on this one. 5, negative 15, 45, negative 35. Well, if you try the arithmetic, negative 15 minus 5 is negative 20. Do you keep adding negative 20 then to get to the next term? No, because then all the terms would be negative. So if that doesn't work, what you try to do then is do right divided by left instead of right minus left. What's negative 15 divided by 5? Negative 3. What's 45 divided by negative 15? Negative 3. This then becomes a common ratio. We call it little r. That means now we're multiplying by negative 3 each time. And we call this one geometric sequence. Now, geometric series is going to be a real important one for us, not so much arithmetic. So we don't have to worry about memorizing anything for this because we know that repeated multiplication is called what? exponentiation. Yeah. So you're going to have this to be of the form negative 3 raised to some power. And then you can just try it out and make corrections. So when n is 1, I have to get a 5? Ooh. Well, let's see. If I plug in a 1 there, I get negative 3. Ooh, here's a cool trick. How about I say that's negative 3 to the n minus 1 power? Now when I plug in a 1, I get 1 minus 1 is 0. Negative 3 to the 0 would be 1. And to turn it into a 5, I'll multiply by it. Does that work? Let's see. Now when I plug in a 2, 2 minus 1 is 1. I get negative 3 times 5 is 15. When I plug in a 3, 3 minus 1 is 2. Negative 3 squared is 9 times 5 is 45. It works. So that's one way to get the nth term. Here's another way. If it's geometric, you can actually factor out the leading term from each term in the sequence. And it makes it a little bit easier. Because then you have a 1 and a negative 3 and then a positive 9, so on and so forth. And now you can clearly see that the 5 is going along for the ride, and now the factor is still negative 3, so now it's negative 3 to some power, and then all you have to do is adjust the exponent so that the first one is a 1. Anything to the 0 power is 1. So you might have to adjust the exponent. We saw that with the even odd numbers. So that's another way to get the nth term. But geometric sequences, and later on geometric series, are very, very important. Geometric sequences are essentially exponential functions. Right? Exponential functions of x end up being geometric series of n later on. It's looking good. All right, the next one. 1, 4, 9, 16, 25. 4 minus 1 is 3. 9 minus 4 is not 3, so it's not arithmetic. 1 times 4 is 4. 4 times 4 is 16. It's not geometric. But what do you notice about those numbers? Those are all perfect squares. Yeah. So 1 squared is 1, 2 squared is 4, 3 squared, 4 squared, 5 squared. So then this one should just be n squared. Yeah, so you could do it like that, or you could say the whole thing is just n squared. Either way, write it as the nth term or write it in braces. Okay, cool. All right, here's the most fun one of the whole group. 4, 10, 28, 82. Well, let's see. 4 plus 6 is 10. 10 plus 6 is not 28. Not arithmetic. 10 divided by 4 is 10 fourths. Is 10 fourths times 10 28? No. But 4 times what number is about 10? 4 times 2 is 8. That's too small. 4 times 3 is 12. A little bit too big. But 10 times 3 is almost 28. And 28, which is almost 30, times 3 is almost 82. So they're closer to times 3 than they are to times 2 times 2. So anybody, does that help anybody? Times 3 minus 2? Oh yeah, okay. So times 3 is 12, minus 2 is 10. Times 3 is 30, minus 2 is 28, times 3. So how can we use that to our advantage? If it's times 3 times 3, if we see the pattern of times 3 times 3, let's go ahead and start off by just saying it's 3 to the n. And then we can adjust. So let's see, if it's 3 to the n, when I plug in a 1, I get 3. What do I need to do to make it a 4? Let's try a plus 1. Now let's try a 2. 3 squared would be 9 plus 1 is 10. 3 cubed is 27 plus 1 is 28. It works. Okay, so plus ... So you might recognize those as being one more than the powers of 3. The powers of 3, 3, 9, 27, 81. These are just one more than the powers of 3. But starting off with knowing it's times 3 minus 2, you get the times 3 part done. And then you can adjust. Okay, pretty nifty. This one, if you ever have like numerators and denominators, and it's not simplified, like 2 once is not 2 and 3/3 is not 1, that means that they're keeping it like that so you can discern the pattern in the top and bottom. So you can think of this as like 2 problems in one. What's the numerator pattern? 2, 3, 4, 5, 6. It's got to be n plus 1. Very good. Because remember, the first term listed always has to correspond with n equals 1. N is an index, essentially. All right, and at the bottom, 1, 3, 5, 7, 9. Yeah, we've already seen those. Those are the odd numbers, 2n minus 1. So again, once you have it, you can always test it out. Try it for n equals 2, try it for n equals 3, see if it matches. And it does. 2n minus 1, not 2n plus 1. Does this sequence converge or diverge? We haven't been asking that question. This converges to 1/2. Good. The others, 3, 8, 13, 18, easily converges to infinity. This one converges by, or diverges, sorry, by oscillation. And it's not between two fixed values. It's between two increasingly large values, like negative infinity, infinity. This one, of course, diverges pretty quickly to infinity. This one converges to 1/2. And then the last one, ln1, ln2, ln4, ln8. I'm going to go on a limb here and help you out and say it's ln of something. I notice that that does not change. That's my contribution. Ln of n squared? Well, that would be when n is 1, I get 1. When n is 2, I'd get 4, not 2. So that doesn't quite work. 2 to the n minus 1. Yeah, these appear to be powers of 2, right? 2, 4 times 2 is 8. So to make it work, when n is 1, 1 minus 1 is 0. 2 to the 0 is 1. Good. When n is 2, 2 minus 1 is 1. I get 2 to the first, which is 2. So there it is. Yes. It's the natural log of 2 to the n minus 1. Sehr gut. So you don't have to do this a lot of the times on the AP exam. But in life, patterns are everywhere. And mathematicians at their most primitive are pattern recognizers. And we try to quantify patterns. Does this sequence converge or diverge? Just think of what the function natural log would look like. It diverges, right? To what? To infinity. Yeah, it diverges to infinity. Okay, we're going to stop right there because that's as far as I got. I had to leave early in the previous class to get that doctor's appointment. But tomorrow we're going to replace the commas with plus signs. And it's a much more interesting question if the sums of these terms converge or diverge. Yes, Meryl? Yeah, absolutely. You could say the sequence diverges to infinity. That would be perfectly fine. All right, let's do what Phipps suggested. Since we have a little bit of time, go to your mode, come down to function, and go over to the last one, which is, yes, switch to sequential mode. Yeah. Yeah, I do. Here you go. You can have the whole pack. Make yourself a double icosahedron. Okay, so notice this. I don't use sequential mode all that often, so I just hit y equals, and I'm actually kind of scared. Notice it says n min equals 1. That's where we're starting by definition. And notice you could see, do you want n or n plus 1, n plus 2? Okay, so u of n. Instead of a sub n, they write it as u of n. Let's do n factorial. So if you hit the x button, you get n. And your factorial is found, hit the math button, click to probability, which on yours is either PROB or PRB, and down there it's number 4. Now, I don't know what, U1 would be the starting value. So you can actually prime it, okay? You can prime it. So what would 1 factorial be? 1. What would 2 factorial be? 2. So I don't know why you have to seed it. Again, I don't do this that often. But let's go ahead and hit zoom or window. Let's go to the window. It starts you off at 1 and it takes you to 10. So that's going to get big really, really quickly up to 10 factorial. And let's just hit, notice x min starts at 0. So it knows that you don't need to look in negative x land. So let's just hit graph. Well, you could see it's getting really big, really fast. Really fast. Okay, so let's do this. We don't need to see negative, so let's go to -1. And let's go up to 1,000. And you can see that it gets really big, really fast. Okay? Remember, for large values, it gets bigger faster than exponential. So let's go ahead and in this one, v of n, let's go ahead and put 2 to the nth power. That would essentially be exponential, right? and see what it looks like in red. So you can already kind of see, and again, what's nice in function mode is the dots are connected with lines. But you can clearly see here that the blue, which is your factorial, is already starting to outpace the growth of 2 to the n, which would be 2 to the x, the exponential functions. Okay? Is it possible to do sequences with not natural numbers? No. Not really. There might be some obscure little vein where you can kind of make exceptions and change the rules. But the reason we use natural numbers is because n is simply counting the terms. The first term, the second term, the third term. So that's why we use n. Now, you can actually use factorial with decimals and fractions, and I don't know how that works. I haven't studied it. But let's do one last thing here, since we do have time. Let's go to the third one, or I'll go to the fourth one because we don't want to graph. Well, that'll work in black. Let's go ahead and graph the Aleph function, which would be n to the nth power. That one should then grow faster than the blue one. Okay, and if we adjusted our window appropriately, go up something higher than 1,000, we might see more dots. Okay, there you go. So the first one, the black dots you can see taking off, that's the Aleph function. It's getting steeper faster than the blue dots, which would be the factorials, and then the slow red dots there would be the exponential. So, and again, if something grows exponentially, that's good, right? But if you can go up to a bank and they say we're offering a special Aleph growth rate, you're like, yeah, I'll take it, right? You come back the next day and you're a millionaire if you put in $1, right? Who knows? All right, any comments or questions? We got sequences under our belt, which is where we carry all the things that we've mastered. Kind of creepy. My grandmother used to carry Kleenexes under her belt. So that, yeah, you never knew Grandma Dottie, but she'd always have Kleenexes under her belt, so if she ever needed one, they're right there. I don't know why the pockets didn't work, but you could say she mastered her Kleenexes, right? So we got sequences under our belt. I don't know where that idiom came from. And tomorrow we'll start series, which again is replacing the commas with what? Plus signs, yeah.